Okay. Okay, good. Okay, looks like it works now. Great. Thanks for having me here. I'm going to talk about a very interesting topic. I think it's also even more so relevant in the area of these large language models, because they seem to be very powerful. And GPT-4 was out last week, and then the vision and literature stuff seems to be really connecting together. And people are like, okay, is it all done, or is there something else that we can do about it, especially in academia? So I thought there is a lot of kind of interesting, also conceptual questions that are not yet fully solved. It would be good to think about it and see, if there's some initial attempts that we can make before eventually, of course, we're going to integrate them with these large models. So in particular, I'm going to talk about what we call this concept learning across domains and modalities. So what is a visual concept? And the notion of a single object like an apple, right? So how can we connect that to all these different types of input that we see, like RGB images, but also what about 3D shapes, the point clouds and videos, and how to connect that to all these different domains? Distill these shared concepts and also to use them in these different domains. Okay, so concepts is very important. We use them in scene understanding. For example, if you show you a picture like this, it's a picture of fire hydrant, and apparently fire hydrants gets much more popular these days because it seems to be an easy object for these diffusion models. So every model we see takes the image and show a 360 view of the fire hydrants. It's kind of funny, but we're not going to talk about diffusion model here so far. So, but still, recognize there is a fire hydrant, and you use this notion. Okay, what is a fire hydrant? You have this kind of symbolic concepts, and you recognize the attributes. So you can use that to answer questions like, what color is fire hydrant? You say, yeah, there's a fire hydrant, and that's yellow. And or how many zebras are there? You say there are like 3 zebras, right? There are also 3 giraffes. Actually, maybe 2 giraffes. But anyway. Okay, so we leverage these concepts in answering questions, but also we use them for different problems. For example, if this is a simple scene where you realize there is a green cube made of metal and rubber sphere, which is red, and we can answer questions like, what's the shape of red object? Okay, the red object has a shape of sphere, but you can use it for other problems like image capturing. There is a green cube behind a red sphere, and you can use it for instance retrieval, right? You show me other examples of rubber sphere. Right, so the same notion of object concepts, really is flexible and use them in a lot of different activities. And so people have always been, even without these large multimodal models, people have been saying, okay, can we have an end-to-end system that would take the image and the language and directly output? Back then it was a single task as a QA, directly output an answer. And nowadays we can do many different tasks with those. And that's kind of nice that you have these end-to-end systems. But sometimes we wonder, is it possible for us to have a little bit more structured representations, or you can say controllability as well into these systems? So we did some initial attempts. That was really a long time ago. It has a lot of limitations, but I think it provides a different perspective that also shows the benefits of actually having a little bit more of symbolic structure. For example, if we show you a picture and the language, and if you can have a very structured representation of the scenes, a green cube made of metal and a sphere made of rubber, and you can do semantic parsing. You can have a structured representation of the question. Okay, what's the shape of the red object? Oh, that means find a red object whose shape is a sphere. And then you query about its shape. Then you can actually take the structured representation and send it to even a purely symbolic execution engine and to read about the answer. And here you don't even need raw sensory input. You don't need a language or visual input. If you have a very structured, it has a complete description, statistics of the input. And the answer will be, okay, this is a sphere, right? So it's kind of very rigid, and seemingly not that flexible representation does have a lot of benefits, especially on data efficiency. If in particular, if you train on 10% of data on this clever data set, actually 1% of data on this clever data set, you already achieve almost perfect, very good accuracy, much better than the baselines. And on 10% data, you're almost perfect, which is while the baseline still doesn't perform as well. Right, so that shows kind of a benefit of a little bit of these kind of structured representations in the scenes, which is very data efficient. But naturally, people will say that is not good enough because it works on these clever scenes where everything is procedurally generated. So of course, there must be a ground truth for this and also for the language. And in this particular case, you sort of know what's the library of possible concepts. You can annotate them. You know the DS domain specific language for the programs. You can generate them. You can provide these. You know there's an underlying ground truth representations for the concepts and programs, and you can have annotations for them. But that's not a case for real world, right? If you have natural picture and natural language description or a question, are the animals grazing? Right. So what is an animal? Which is kind of really hard to describe. It's not like in cube, it's a green or not green. You know, and also how to really describe an animal from these real images and textures. And the definition of grays can annotate programs for them. So I think there's a lot in defining the concept annotations for scenes as well as the program annotation of the language. So how can we scale this approach, you know, to real images? So nowadays, I would say there's kind of more solution, which is, for example, you can say, okay, what if we just use things like Viper GPT or visual programming, right? Programming, you know, they won this best paper award at CVPR or something. So, you know, you can say, yeah, you know, I can OpenAI Codex, this large preaching model to actually generate a program. And then I can just run it with visual input on this large vision language, and that will give you, right? So you completely leverage these powerful data-driven models, which I think they're really doing very well. But the limitations here is the whole process. It's you're not even fine-tuning it. Right? The whole process is inference only. You take all models, you run OpenAI Codex and give you a program, and then you run it on images, and that give you the final output. And you know, you take these models, but what if you want to sort of adapt them? First, you can't really train them, right? Unless you're OpenAI or Google or Meta. But secondly, even you can't really think about if I want to switch to a slightly different domains. Now, you know, if the input is not an image, what about if it's video? Or video, maybe you can still fine tune a little bit because you can have previous models on videos. But what about if the input is a 3D point cloud or something? So, or at different domains like cartoons. So if you want to adjust and fine tune that to a different domain, that's already very, very hard. And that the whole system here also that includes a lot of modules like when the output program, you know, maybe they use primitives can be like an object detector or something, which is not even differentiable. So that really makes it impossible to, you know, fine tune these specific modules for any new domains. So I think the modern solution is really powerful, but we can probably do a little better than that. So that's why I want to bring back this kind of old, which is not even that old, which is 2019, but 4 years ago is, I think, considered Asian in this deep learning field. But can we actually do some sort of joint learning of concepts and, you know, the parts of the questions? So if we don't have annotations on concepts or programs, we don't have annotations on either of them, but we can think about, you know, doing things like the bootstrapping, that is how the learning of one the other, right? How program learning may help concept learning, and how concept learning may help program learning. So I'm going to first talk about our work that was kind of a little old, but also I will later show that how we can modernize it, contextualize them into this modern framework. Okay, what if we have LLM, how to integrate them and make them a little better? Okay, so what does this bootstrapping thing really mean? How could these learning help each other? So let's go back to this simple example. I can give a concrete illustration. You have an image and you have a simple questions. In this particular case, of course, you want to learn some representations for objects. You want to no longer assume you know the library of concepts. So it's not like object only be red or green or yellow, but instead you have these representations that are being learned from the images. And for language as well, you know, you have two things. The first is you want to sort of understand the meaning of the language. Okay, what's the shape of that object? Means you want to find something that is red and you want to find its shape. Also, at the same time, you don't want to assume, you know, you already know the concept, so you don't have to assume what red already means. You want to learn the meaning of red at the same time, right? So here, there's no preaching, you know. Can you also discover, you know, what does red mean? Can you learn embedding for the words as well? And then at the same time, you have this form for the language. So what's the shape of red object means you want to find something that is red, whatever that means, and then you write whatever that means. Okay, and then you can send all these learning embeddings and this semantic form into a neural symbolic reasoning module, which is essentially a neural network, but approximating different symbolic operations so that it's still end-to-end differentiable. That gives you an answer that is a sphere. You can train it, you know, okay, giving final answer to a sphere, and as I'll show later, how you can learn these systems. But in this particular case, you know, the concepts has two categories. One is the representations for objects and the visual concept. And the second is the representation for the word. So that's the linguistic concepts. And the program here is just the structure form for the question. So in particular, I'll talk about this direction. The program learning can help concept learning. It's very relevant to the things I'll talk about later and how we later integrate and contextualize them with large language models. So how can we do that? Here we assume we already have a very good program. Okay, we already can magically parse the sentence. Okay, what's the shape of the red object? Oh, it means find something that's red and pair its shape. But how could this structure form and the question that's maybe like a modular neural network that takes this object representation and outputs hopefully another representation which is more aligned with the color of objects. And then you can do that for the other objects. You can compare that with the embedding of red, and you find that, okay, the first object seems very different from a red object, and the second object seems very similar to a red object. So it's much more likely that a second object is a red object. And you can go from there, and you can, now I want to understand its shape. So you can take the embedding of the object 2, and then you pair its shape, go through another modular neural network, but actually they can be one network, just conditional on different input. And you can compare that with the embeddings of different words, different concepts, and you find that object 2 is not likely to be a cube, much likely to be a sphere, and less likely to be a cylinder. So that really gives you the answer, okay, how you can actually leverage the program to execute the concept embeddings. And so your system will be able to output something, and then you can compare that output with the ground truth, which is your supervision. That's a kind of a weak and distant supervision. But that gives you some signals about, okay, what that correct answer should be. And all these execution steps, again, as I said, is kind of smaller modular neural networks that are approximating these symbolic executions, so they're end-to-end differentiable, which means you can actually use that very weak for backpropagation and for learning and updating the concepts, right? So you no longer have to assume the concept's kind of pre-trained, but or it can be pre-trained actually. Although in this particular work, when we do it, we want to just do everything from scratch, so nothing is pre-trained. But it can be pre-trained even. But you can now update and keep learning a better visual concepts for them. So that's how program learning may help concept learning. Okay, so we'll see later that this actually can be more than nice, because back then, for example, for semantic parsing, we use whatever is off the shelf thing from Stanford NLP group. But now, of course, you can use OpenAI Codex, which gives you hopefully a much better semantic parsing. And there's another direction, how concept learning may help program learning, which is equally important and I think very interesting, but it's a bit less relevant here. That involves some reinforced learning, so that you can do better structured discovery, which I think we can talk about later offline, but I'm not going to talk about it here. And in this particular context right now, if everyone's using LLM, it's just really hard to find an LLM. So that's a bit less relevant. But again, we can, maybe in the longer term future, it'll be more relevant. Okay. So how concept learning and program learning may help each other, this sort of completes the loop. And this is really work done by Jiajun, who is a PhD student at MIT, but back then she's an undergrad working with me. Okay, so benefits of that is you still have very high accuracy. It's almost as good as better than these end-to-end baselines back then, but also fully differentiable. And it's very data efficient. If you train on 10% data, it's almost perfect as a purely symbolic methods, but much better than the baselines. This kind of structured compositional representation allows you to do combinatorial generalization, that you can train on simpler scenes with simpler questions, and everywhere, every method performs equally well, roughly equally well, but you test them on more complex scenes with longer questions, you can do almost the same, you have almost the same performance, while the baselines don't perform that well. You can now really, it's applicable to real world scenarios, right? Because you no longer assume you have the library of concepts on annotations on either concepts once. So you can really execute on the image I showed at the very beginning and say, what's the color of a fire hydrant? You will find the object that is a fire hydrant and give the answer that is yellow. Or you can find objects that are zebras and give the answer that is tree. You can do also a concept retrieval, like finding other horses, finding other people. Or again, this thing is compositional, so you can see, okay, what are other examples of persons on the table? Okay, 15 minutes on old work. But that's, I thought, really important, because that lays the foundation of the new work that I'm going to talk about, and how we're able to bring this, like, I don't know, more modern in the sense that you must have an LLM somewhere. So before I even talk about that, let me show that how we can use this kind of neurosymbolic concept learner, not only in the domain of just 2D question answering and reasoning, but also in other domains. So since then, we have been, more or less trying to extend the work in different directions, including how this can be applicable to dynamic scenes, and how we can go from 2D images to 3D scenes for 3D referential expression grounding, visual reasoning, how we can use it to understand human motion, as well as eventually how the concepts can not only be static or dynamic concepts, but really be action concepts. So that when you say, I want to grasp this thing, of course you want to just recognize that, oh, that's a grasp. You want to retrieve other instances of grasping. But you also want to do a little bit more, because when I say grasp something, I say, okay, I grasp this cup. Then you can recognize that's a grasp, but you also, if I'm a robot, then you want the robot to sort of learn action policy, right? So what are the actions I should take? What are the action parameters the robot should take? So to really reach the object and to grasp it. So extend that to the domain of robotic manipulation as well. Okay, I don't have that much time, so I'll just very quickly show some highlights, one slide, each of these directions. But I'm happy to talk about this offline. So first on dynamic scenes. So here's a dynamic video of objects interacting with each other. And is it playing? Okay, great. So here you can ask more interesting questions beyond like what's the object that is there, what's the color, right? You can of course do temporal reasoning. What shape is the second object that collides with the sign sitting there? So you have to understand this temporal order. What do you mean by second, or what do you mean by first, or what do you mean by last? But you can also do some sort of causal reasoning as well. For example, objects are responsible for the second collision. So you have to be really careful with the language here, because when it's A causes B, that means many different things. We sort of want to avoid that, and we say, well, object is responsible, but that's still not perfect. So anyway, but you sort of get what I mean. You just understand why the things is happening. You can do predictive, like what's going to happen next if the objects keep moving. And then you can also do, it's very important to differentiate predictive or hypothetical versus counterfactual reasoning. That is, you really have to, it's not just predicting what's going to happen, but really have to see events, but then let's say, okay, well, what have happened if the object were not there, right? So it's really a counterfactual simulation. So you can do these kind of reasonings. But back then, there's no even data sets for it. So what we did is we built a data set of 20,000 synthetic objects with 300,000 questions. We call this clever data sets. And it, to solve this problem, we actually built a model for it, but I decided not to talk about it. So it's a bit complicated in a separate paper, but we can talk about it offline. But the key idea here is you really have to, understand not only static concepts like yellow or a graph, but you have to understand there are dynamic concepts. For example, if I ask you what happened next, then you say, okay, of course, the answer is the blue sphere and the yellow object collide. But you have to, of course, understand static concepts of what is a blue sphere and what is a yellow object. But you have to also understand actual events or dynamic concepts, right? What do you mean by collision, right? So collision is a kind of a binary predicate that you can ground onto the two objects, but really the temporal sequences of the two objects, not a single snapshot. Okay. So you're welcome to use the data set, and you're welcome to do it on top of our method. We proposed the method like a year and a half ago. By now, it is definitely not the best, and I think we have a leaderboard and people are doing better on that. So you're welcome to give it a try. And more recently, we've been doing that in 3D as well. So if you want to do visual reasoning, so here, you can think about it. It's very easy to draw the analogy here. Now the input is no longer image, but some sort of point cloud, right? So you have an input point cloud, and you want to reason about objects and the relations, and then you can have structured representations, symbolic programs for the questions, and then you can execute the programs and give you do referential grounding. Let's say, okay, if I give you a scene and ask you, okay, here you have to really take into consideration where's the viewpoint, right? So facing the front of the shelf, where's the viewpoint of the camera situation, and then you want to select the door that is on the right side of it. Right, so you have to, how could you actually extend the system going from 2D images to 3D plan clouds to do these kind of grounding, but also later question and answering on 3D scenes. And here is, for example, a demo. That is, if you want to facing the couch from the side you sit on it, we want to choose the cabinet that is on the right of the couch. So you want to, first find a couch, and then you want to, at the same time, so okay, you want to choose the cabinet. So, but there are multiple cabinets. So how could you actually, given the information of the couch and the instructions, and the multiple cabinet candidates to find a cabinet that really satisfy these constraints. So we sort of extended our earlier system from 2D to 3D, but we did, of course, we did some changes. For example, instead of using off-the-shelf semantic parser, we still use the off-the-shelf semantic parser, but here we actually did use OpenAI codecs for generating those kind of programs. So you can do that in 3D, and it still has the same benefits as before in the sense that it's very data efficient. If you train it on 1% of data or 10% of data, you can see that our method is much better. And if you train a full data set, it is slightly worse, more or less comparable, but slightly worse than those end-to-end neural methods, but it's much more data efficient. It shows some generalization. For example, if you train on a set of scenes, but you're doing testing, you test on scenes with novel pairs of object co-occurrences, there are objects that appear together, you never see them in training, you can still do much better in this kind of generalization, or you generalize much better to just totally new scenes. So I think the system which call neurosymbolic bounding for 3D is still excels in data efficiency and generalization. And similarly, you could combine dynamic data reasoning and 3D reasoning, and a perfect domain would be human motion. And so I'm going to not talk about the model here, but just to show that we also build a data set for it, for really real-world human motion sequences, where we paired real-world human motion sequences from mocap data with human question answering from real humans, so that we have a realistic reasoning on real human motion, so that you can do a lot of interesting reasoning question problems on it. And this paper was just published, and you're welcome to use the data set and build on top of it. And finally, a little bit about robotic manipulation. So of course, eventually you want to always go from perception to interaction. And so here we're sort of like advocating a style of primitive-based robotic manipulation. So you want to learn policies that map from states and goals to the next actions. So how can you pack the yellow flower into the brown box, or you can push the green box into the blue sphere. So compare that with this kind of end-to-end model. That is, there's a huge model that is pre-trained and you want to fine-tune it. So the difference is, in these kind of models, you have already seen there's an image, and you send it to your pre-trained image encoder. You can send a text to a pre-trained text encoder, and then you have a small neural network that tries to decode control parameters. But here we have a more structured representation. For example, in the case of put a heart into the hole. So you want to understand, okay, there's an action of a put, and your goal is find something that is heart, and you want to find something that's hold the thing into a hole. And then you can actually send these kind of specific primitives into corresponding modules for example, locating, finding the holes and parts, and for actually, performing action like the do module has action policy associated with this, where it actually can perform the task for you. So an illustration of how this will look like is, for example, if I show you an image and ask you to pack the blue hexagon into the orange box, then what you can do is you can find a hexagon which is blue, you can find a box which is orange, and then finally you have these kind of attended feature maps, which you can see they're actually pretty interpretable and perform really well, because here that's where you really leverage these large pre-trained vision models, and they're supposed to recognize very well and also generate new objects. But at the same time, you have this modular decomposed representations, and then you can finally send them to an action module that learns how to pack it, that basically outputs the parameters and saying, okay, where the robot arm should go to really pack the objects. So, okay, the pick and place action, where it should take place. And it really, similarly, this thing we call, inspired by clipboard, right? So we call them program port, which also enables strong zero-shot generalization and compositional generalization. For example, if we train them on things like pack the yellow flower into the brown box or push the green box into the blue sphere, you can generalize them to a new object, right? So where is the new generation coming from? Right? If you look at all this, from let's say clipboard, but even more recently to the RT1, RT2 stuff, a large part of it is from, of course, these vision language models have seen these words, and they're supposed to know what a ring is, what a new word is, then we generalize it. So generalization really comes from this pre-trained knowledge, these pre-trained models. So here, by sort of disentangle that a little bit, let this pre-trained model do the job that they're good at, you still get all the benefits of this type of generalization. You'll be able to see, okay, this new object is rain. I don't really know, I've never seen it, but my pre-trained model have read the word rain and have seen what a rain looks like. You should still be able to generalize and to pack the rain into a brown box. So you have the same, generalization ability. But gives you much more interpretability about what the object is like, and also gives you better data efficiency. Another type of generalization is, of course, compositional generalization. Like, okay, you can, during training, you always put object A into brown box and put green blocks into the blue sphere. But during testing, you can also do something that is compositionally new in the sense that, okay, you can push the yellow flower into the blue square, which is a novel combination you've never seen before. Okay. So that's all kind of different types of extensions that we've been trying, extending these systems to different domains. So that seems great. We can do everything in 2D now. We can sort of do things in dynamics, scenes, videos, 3Ds, or 4Ds, or even robotic manipulation. So now we have the question of what's left, right? Is the problem all done? We thought, there's something that is left, that is not really being solved. And if we look a bit more closely to specific instances in these different domains, then we realize we can actually dig a bit deeper into it. For example, let's just take left as a concrete example, right? If I, the word left itself is kind of left and really unexplained, because if you look at it, it appears in all these different domains in different ways. In the 2D domain, I can ask you, is there a red sphere to the left of a large sphere? In the 3D domain, I can say, is there a dresser on the left of the cabinet? In a temporal sequence reasoning, I can say, what part do they use before they move to the left? Or in robotic manipulation, I can say, put T to the left of Y and A. So the same word, left, appears in different domains. And there must be a reason, right? So why I use the same word or same concepts in these different domains? It cannot really mean things that are totally different. But also it means slightly different things in these different domains, right? In 2D, it's very easy. If I ask you, is A on the left of B? You just look at their bounding boxes. You compare the X coordinates. Okay, the coordinate system, you take out, okay, this one is, 100, that's 200. So A is on the left of B because the coordinates, X coordinate is actually smaller. But in 3D, that is slightly different because you have to think about your own viewpoint, right? You have to take viewpoint into consideration. There's no 2D bounding boxes anymore. You have 3D bounding boxes, but the problem is not as simple as just comparing the coordinates of the 3D bounding boxes, because you have to take viewpoint into consideration. If I turn around, then something that A is on the left of B becomes A is on the right of B. So there are multiple, I would say, they're kind of subtle, but clearly different and domain-specific groundings of this word in these different domains. But also there's something that must be shared across these different domains, because there's a reason that we all call them left, and there's a reason that all these large models can generalize, because something that is red must share something that is similar. So can we have a better representation for words like left, or for any words, but really captures the best of both worlds, the part that is domain independent, the part that's domain dependent or domain specific? So I'll say, there is what is being shared. Independent is the domain independent reasoning. You can actually do pretty well using first order logic. Is there an object to for example, if I ask you, I can ask you sort of like really the same form of questions in these different domains. Is there an object to the left of the target? And in all these cases, the meaning of left is, okay, you want to find an anchor object, which is the target, and you want to search among all other objects, right? The X, is there any object X that which, when you compare that, you combine that with the anchor object Y, then both of them, they actually satisfy the predicate, which is a binary predicate left. So, the specific meanings of left, it can be grounded difference in every domain. If it's 2D, if it's 3D bounding boxes, if it's robotic actions, it may mean something that's slightly different. But general form, which you represent very well using first order logic, is really universal, and it's kind of shared across all these different domains. And I would say probably also generalized to other different domains, right? So the domain independent reasoning part can actually be written out like this, right? Is there exists any objects at X which it satisfies the binary predicate of left, where there's a target object, anchor object Y. And let's see how this form, can be actually grounded to these specific different domains. For example, in the case of 2D reasoning, then basically you're searching for the X here is, okay, is there a red sphere? So you want to find an object that satisfies the predicate of red, whatever that means, and the predicate of sphere. And you see if there's an object that satisfies this binary predicate of left. If you learn it in neural network, for the neural network will automatically figure out it should just be compared to 2D coordinates in this domain. And then, okay, in this case, the answer is yes or true. But in the case of 3D, then the unclaimed object Y becomes the cabinet. And now here the question is, can I find another object which is a dresser, or whatever that means, will also satisfy the predicate of left. Here, the left means something that's slightly different. And now you have to take into 3D coordinates into account, you have to take your viewpoint into account and stuff like that. And the answer here is true too. And that's the similar case, for human motion understanding. Here, left, you have to, the input becomes human motion sequences. So of course, you have to learn the different features on top of it. But still, you want to, you will be able to just, ground that into the same shared first order logical form for reasoning, as well as in the case of robotic manipulation as well. Well, the only difference is finally during the execute predicate, you actually output control parameters so that the system not only just output yes or no, but also at the same time output control parameters so that the robot can actually pick up T and put it to the left of the YA. So now we have this kind of new observation, which I thought is very interesting and exciting. Then there seems no reason that we build these different systems for different domains. They're nice, but there should be able to have one unified shared representation for all these different domains. So that's what we call this system. We also call it left, but now here it means logic enhanced foundation models. So think about how we can take these foundation models but enhance them, with the structured form, which in this particular case, we use this first order logic. So our goal here is to really have a unifying framework for concept learning and reasoning across all these different domains and tasks. So it consists of both the domain independent reasoning module, which has an integration of foundation model interpreter and a differentiable. That's important. So let's make it actually just like earlier in NSCL, we said it exists and all these things, we made them differentiable so that you can do backpropagation for learning better concepts. Here, the first order logic executor also made differentiable, so allows you to actually learn specific domain-specific groundings of lab. So the predicates of lab can be different in different domains. That's fine, because you can learn in the different domains with the help of these differentiable logical executor. And at the same time, you learn these domain-specific grounding modules from each modalities. And our hope and what we can achieve is actually also a strong performance across these different domains. It's very compelling generalization. We keep saying good performance, data efficiency, and strong generalization to different domains. This is done by Joy Su, also with others like Jiajun I showed before, but Joy Su, who is my PhD student, is doing great. Okay, so people are saying, okay, so what are the predicates or what are the logic you think about? So is it like domain specific? It's not domain specific. It's like you open any logic textbook, you find it. Okay, it's the first order logic, which is all the primitives are listed here, and they're all implemented differentially. It can train on different domains and tasks with no predefined DSL. So people are sometimes saying, oh yeah, if you work on 2D, you work on 3D, you work on human motion, every domain you have to design a specific DSL. That's really not very general. If I give you a new domain, you have to first write down what a domain specific language. That's just really not very general. But actually, here, you just need this logic textbook, and you don't need anything that is predefined, the DSLs, and you don't have any specific program implementation for each domain. It's just all very universal. And it has this model itself has this domain independent LLM-based interpreter, which outputs this first order logic form for the questions. And then you have all these things on the top right, which are first order logic executors that are implemented differentially, but there's no learnable parameters. So you don't really have to worry about how to learn these things, but they're differentiable, which allows you to learn the domain dependent part, which is the bottom right. Okay, what does sphere mean? What does left mean? They may mean different things on these different, at least the input modality is different, right? The 2D images, point clouds, and motion sequences. But here, allows you to learn the specific groundings of these predicates into these different domains. And the boundary models may look different, depending on input and 2D, 3D motion sequences. You may have different encoders to learn to ground these different modules. And you may compute the unary or binary or ternary features, because sometimes the features, the predicates are left, it really involves two objects, right? So you need binary features on there to think about the interactions between two objects. Okay, so you can learn to ground these different domains using possibly different feature encoders for these domains. But what is shared is that first order logic, program executor, which is differentiable. So it does perform pretty well across different domains. It's one unified framework. It's efficient concept learning across the 4 different domains: 2D, 3D, temporal reasoning, and robotic manipulation. It achieves very good performance, better or at least comparable with the thing that people have developed before, including both end-to-end methods or the prior neural symbolic methods that we've been talking about. But unlike the prior methods, which you have to define something that's more specific for every domain, there's no predefinition of DSLs anymore. And it is just a shared framework with no additional predefined DSLs for each domain, so it still performs really well. It is also very data efficient. If you train on 10% of data as before, on clever reasoning, you can do equally well. And this is in 2D, and on the right, this is in 3D. So you can see that on 0.5% data, 1.5% data on 2D Browning and 3D Browning, it is also much more data efficient than end-to-end methods. And these are like really the most recent methods now, because this paper was just published at NeurIPS. Actually, it's not even archived yet. We're going to archive it like this week or next week and release the code as well. Okay, the zero-shot generalization to novel tasks. So what we tried is, okay, if we train on Clever using this new framework, but you test it on different variants of Clever, where they have just like different designs or different reasoning problems you want to think about, and you compare models like visual programming or GPT, which was just published CVPR, then you can actually do much better in generalizing to these different domains. This is actually because it allows you to adapt to these particular domains in the sense that you can actually fine tune and you learn better representations, what, for example, left means in this Clever domain. So it allows you to do much better generalization to novel tasks. Once you have adapted on Clever, you can transfer much better to other Clever variants. And I think this is important to show that people are always saying, okay, if I show some logic, people are like, I'm going away because it seems very hard to implement. It's very hard to optimize. That's first optimized part is totally not true, because now, as I've been keeping saying, everything is differentiable, so you optimize it with gradient descent. There's nothing fancy. The second part, people are saying, okay, but that still seems very complicated, hard to use. But that is not true either, because for the first logic part, it was implemented and was specified implementations. It's differentiable, but none of them are parameters, but you can just take our off-the-shelf implementation. And the second part is implemented with neural networks, but you can of course replace that with your own neural network encoders for different diffuser domains. And think about it in this way, that is, okay, you can even replace, here we probably just use different type of small neural networks like MLPs, but you can replace that with also preaching networks like, okay, what if I just use the object detector or stuff, or planner, stuff like that, right? You can even use those non-differentiable stuff, but the fact that using these non-differentiable stuff is you won't be able to fine tune anymore. So think about it as, if you, instead of using our framework, actually not, if you use our framework, but you replace the feature encoders for spheres or left with object detector for sphere, right? So instead of having sphere X as a learned module that is joint chain trained or fine tuned as in our framework, but let's say now whenever I output sphere X, I just want a feature object detector which detects sphere for you, then the whole paradigm degenerates into visual programming or GPT. Right, so it's exactly the same as all these non-differential or inference-only paradigm. The only difference is you can think about it as a more generalized version, which gives you the additional flexibility of fine-tuning and adapting to different domains. But if you don't want to do that, or there are cases where you may want to not want to do that for specific domains, you can actually don't worry about it and just use, just relax that constraint. So this is really a more generalized version of that. Instead of a more constrained version. So I think it's important to emphasize this difference here, that it just, you can also use, for some of these modules, maybe you can say, oh, I know some things that's just too complicated. Let's say there's, I don't know, an elephant, which is kind of hard to describe. And I feel like I'm confident I have the best elephant detector, which works 100% of the time. And I'm not going to need I don't need any help in detecting elephant. I'm sure my elephant detector is the best in the world. You can use that, and you can, for the other modules, you can still use, these neural network predicates that you can actually learn to, you can actually let them work together, but you only fine tune the non-elephant detection modules. So this is really a very flexible framework, much more generalizable and flexible, hopefully, than visual programming by GPT, but also important, very easy to implement. So code is very simple. So just a few lines of code, so everyone should be easy to use it. Hopefully after release next week, in the next maybe 2 weeks. Okay, I'm out of time, but I'm also done. So okay, there is a a small issue on the animation here. But I'll just say the points that we want to, that is, what are the fundamental questions we want to address here, right? There's this, learning versus modeling question. There are people, it's kind of interesting, that is, if we look at the entire bit about doing machine learning, then, of course, we all know there's no free lunch. So you need some level of inductive biases, right? The people saying there's no inductive biases, that's impossible. You can't really do everything with the MLP. So there must be some inductive biases, but there are a lot of people is attention is all you need, or I can say convolution is all you need. All you need is this kind of spatial locality, temporal locality, or self-similarity. Or there are people who is on the other extreme. For example, maybe Josh gave the opening remark, right? So he will probably say, oh, actually, you need much more. You need the entire, to do this centrally. Well, that's probably true, but then these things makes it very hard to optimize. And at the same time, we have seen that these data-driven models are very powerful and clearly want to do is to think about what are the right inductive bias. Allow it, but also at the same time to put in the right for a particular domain, of course. So then what are really the minimal, but also very universal structure that we should put into it so that it's domain independent, and really helps us to generalize to new domains and passive modality? I think that's a fundamental question I want to think about. In this particular talk, I talked almost entirely about concepts. What is the concept and what is the word and how to represent it and what is shared for the word, not shared for this word representation, for the concept representation. But there's also equally important and maybe more important questions on 3D perception, modeling, inverse rendering. But I think that's all the fundamental questions I want to understand. I think the principle here, at least what I'm trying to say, is think about things that are very minimal, but also really universal. And if it's true and applicable everywhere, then it shouldn't really hurt your generation. It should really help you. And I think also final sentence is a large part of it will be and could be inspired by concepts. So I think we should all listen to this practice talk afterwards. Thank you. We are really running out of time, but we can
all his work seems very perfect. But I wonder if you do predicate intelligence, which in terms of the work, maybe means coming up with new concepts on the fly. So I do wonder if you do predicate intelligence, and if you do, can you briefly explain how it works?
Okay, that's important. Okay. So there are two aspects of the question. So first, I just want to confirm with you, you said predicate invention, right? Okay. I think it could mean two different things. So the answer is yes to one and no to the other one. Actually, maybe no to both of them, but potentially yes for one of them. So no, predicate invention can be two things. One is where's the predicate coming from, right? So should there be what does the lab predicate come from? Why do you care about lab or not lab? And can you come up with a new concept? Here in this case, no, because we're saying where the concept coming from, where the predicate coming from. Very simple. It's informed by language. So it's kind of a natural supervision in the sense of language. There's a reason that you invent a word because you want to refer to something that is, at a certain level abstraction that is meaningful and pragmatic to come up with a new word. So the creation of language already did this for you. So in that sense, we're not really coming up with new because the predicates here are already formed by language. And there's a second interpretation of the question is, you can say predicate invention means, okay, how this form can be invented, or can you come up with, maybe there are, think about it as, programs can be very complex, but maybe there could be some hierarchical structure, and you can come up with some new intermediate level of predicates, which is a higher level abstraction, and you can gradually build on top of it so that you can represent complex concepts, but maybe with different types of subroutines. instructional concepts in the sense that, like, no, I think that's interesting to look at.
Thanks so much.